We saw Fourier transform and phase estimation before. As mentioned, these were the basic building blocks for the future algorithms to come. These were in itself slightly natural problems and they had some classical counterpart which they solved. But we are more interested in classical problems in themselves, like Shor's algorithm for factoring, Rover's algorithm for search. We will take a path now which will take us towards Shor's algorithm. This is the polynomial time algorithm for factorization. Importantly, no such classical algorithm is known. This is one example where it seems that quantum algorithms do much better than the classical algorithms. If we look at Shor's algorithm, it is one of those Fourier based algorithms. These are a long list of algorithms which you can perform using Fourier transform. Our goal would be to understand many of these algorithms and then take the path to Shor's algorithm. So you have to do some background, and for that, for this Fourier based algorithms, we'll start with one of the simple one, which is called Simon's algorithm. This was given in the early days of quantum computing, and again it gives us separation in the query framework. Remember, we have already seen some algorithms like Deutsch-Jozsa, Bernstein-Vazirani, where we got separations between quantum model and deterministic model, or quantum and randomized model. Specifically, if you look at Bernstein-Vazirani algorithm, it was solved using just one quantum query, but it required at least log n randomized queries. You might say that this is not much, this is just the ratio of log n. On the other hand, for Simon's algorithm, the difference is going to be huge. Quantumly, we will just be able to do it in log n queries, but randomly, it will take at least square root n queries. This would be an exponential separation. Even if we did not want to learn about Fourier-based algorithms, Simon's algorithm would be nice to see because of this separation achieved. This was its purpose in the beginning, and we are going to see how this, what the Simon's problem is and how it is solved with such a remarkable difference between the quantum query algorithm and the randomized query algorithm. Let me describe the problem first. We have to be more careful this time. Again, let's say that my input size is n is equal to 2 to the power k for some k. In that case, my x is going to have n indices, x1 to xn. Again, I can view it as an index which is in this set. It can be thought of as an index, or I, where I say, oh, look at the bit xi, I can also be looked at as a string of length k, like 0, 0, 0, 0, for example. This is the setting which we have seen now. The only difference is that xi itself is going to be an element of n. If you look at the previous settings like Deutsch-Jozsa, Bernstein-Vazirani, generally our xi were element of 0, 1. This was the case for Bernstein was Rani, or Deutsch-Schulze. But for Simon's algorithm, it is going to be slightly different. Xi is element of n. In other words, I can say that if I want to talk about my input, this input is element of n to the power n. This is one way to think of it. It is a string of length n, like last time, but each element of the string is not just 0, 1, it takes value in this set. Notice this difference. The output in some sense is pretty big. Remember, we had the same functional definition in this case. We always said that when I looked at a string like this and n is equal to the k, I could have interpreted xi as f of I. Here I was an index, here I was a binary string of length k. They have one-to-one correspondence because n is equal to 2 to the power k. This way I can think of the problem as I have a function, I can give an index, and then in Deutsch-Schulze the output was a 0, 1 thing. Now I get an output fi which is an element of n. This is the important difference. Like last case, we are going to have the promise. The promise is that xi is equal to xj, which is same as saying fi is equal to fj if and only if I is equal to j XOR s. When I write this equation, I am viewing I, j and s as Boolean strings. Hence, I can define the XOR operator between these ky strings. These are element-wise XORs of j and s. If this happens, then xi is equal to xj. The trouble is s is a hidden shift and no marks for guessing it. What is Simon's problem? Simon's problem is to guess what is s, the hidden shift. This is the question which Simon's problem asks. Let me once again reiterate the problem. I am given an x which is now n to the power n, where I can interpret x as x1 to xn, and then the promise says that xi is equal to xj if and only if these coordinates are related by a hidden shift. The question is to find this. In this way, you can say that there are n indices and the query complexity could be at most n. What we are going to see is that we are going to solve it in log n quantum queries, but it will require at least square root n randomized queries. This is to solve Simon's problem. This is the exponential separation which we want to get. I have not come to the algorithm yet, but just telling you the importance of this result. We wanted to figure out the hidden shift. This S was called a hidden shift. The objective is to find the hidden shift given the oracle access to this string X. In this case, if you think of it, even our oracle is slightly different. I can think of it as a function or as X. Let's keep the same interpretation as an input. When I give I, it returns me xi. That is the classical input. The only thing now is that xi is not a binary string. It is an n. So even xi can be thought of as a k-bit string. Now you might ask that our query oracle is not Boolean. Probably that's the reason why you are getting that shift, getting that separation. It actually doesn't matter. You can think of your input x as having k times to the power k indices. The reason being, I had 2 to the k choices, n was equal to the k. Each xi can be thought of as a k-bit string. I can think of my entire input as a k-bit string. I'm sorry, I can think of my entire input as k times to the power k-bit string. Then it will be Boolean input, Boolean output problem. And notice that I can still do the same thing using log square n quantum queries. Because whatever quantum queries, one quantum query would have been equivalent to k queries now. When I write everything as a bit, when I'm only allowed to query a bit, even in this case, only log square n quantum queries are enough, because one quantum query in the previous case will be equal to k quantum queries, because one index is k bit long. So I will take log square n quantum queries. On the other hand, this root n randomized query thing will remain, will show that at least one of the blocks of that root n, one of the things has to be queried. So this bound will remain the same. So the exponential separation still holds true. I need not worry about this point that I'm thinking of xi as a value which can take up to n values. It doesn't matter. Even if I convert them into Boolean values, still my exponential separation remains. If you are not worried about it, then great. Then let's look at the algorithm. Our promise was that if I was j plus s, if and only then xi is equal to xj. The algorithm is not going to be very different from whatever you have seen before. Remember that we start with state 0, 0. The only difference from Deutsch-Jotza this time is that this is going to be an index, so this will require k qubits for index. But even this now is the output of the oracle query. Even this will require k qubits now. This is not should not surprise you. This is because even to write xi, I need k qubits. That's why I will start with 2 k qubits, all in state 0. Independent of the second register, I can convert it into an equal superposition. That can be done using Hadamard. This will give me 1 over square root k summation over j to 0. I can say that my j goes from 0 to the k minus 1. This is the step which we have done 1000 times even in Deutsch-Jotza. getting equal superposition over all the indices. And then we query the oracle. This should tell us the function value or the xj's as we noticed it. Again, this step is similar to what you have seen before. It should not surprise you. Only difference is that this xj is now k qubits instead of just 1 qubit, as in the case of Deutsch or Bernstein. This is a common step in almost all the algorithms, and you will see there is a good reason for it. There's a good reason why we always end up with these two first steps. We will abstract out these steps and we will say that we can solve a much more general problem like that. But that's the topic in the next talk. Let's focus on Simon's problem. You start with 0, 0 state. In the first step, you apply Hadamard. That Hadamard gives you equal superposition. Then you query the oracle and you get this state. Now something different is going to happen. Now I'm going to measure the second resistor. In this case, if I measure xi, the first resistor should have a value. This might take a bit of thinking, but make sure that you are convinced. You can pause the video at this point and see that this is going to happen. The reason is that you are measuring, you will get one of the outputs. You are measuring in the standard basis. Hence, you will observe one of the outputs, one of the xi's. But if you observe xi, then you don't know whether the first resistor was an I or was it an I plus S. Both these first resistors could give you xi. So my state is going to be 1 by root 2 I plus S. You can think of it as the projector on xi, identity tensor xi. If this is the projector on this state, you will get 1 by root 2 I plus S. You can convince yourself of that. Now, one thing which is kind of side thing is to ignore xi. But important thing to remember here is that I have this state which is somehow related to S. I get only two things which are related by S. If I measure, the first resistor, it is not going to happen. Because then I will lose this dependence. I will get either I or I plus S. I don't know which one it is. And I lose all the information. That should not work. Now what we are going to do, we are going to do what we know. We are going to do a Fourier transform. Remember the state at this point. It is I plus S for some I. And actually, if you think about it, this I is chosen uniformly at random. Let's apply Fourier transform. A good question here would be, which Fourier transform? It has to be Z2 to the power n. Once you apply Fourier transform, you will get this state. This is from all the formulas which we have learned till now. It should not surprise you. State I will give you this phase, and state I plus S will give you this phase. and I should say that this is the phase for state L. This is my complete state. You can convince yourself by reminding yourself of the Fourier transform. Now, what are the amplitudes for state L? Notice that L amplitude has only two possibilities: either it is 0 or it is 1. I'm talking about this part, forget about the normalization. This amplitude is 0 if S dot, or I should say I dot L is not equal to I plus S dot L, which is equivalent to saying that S dot L is equal to 1. Notice that S dot L can only be 1 or 0. There are only two possibilities. If it is not equal, then S dot L should be equal to 1, and L amplitude is 2. Again, I'm not talking about the normalization here, just this thing, if is equal to I plus S dot L. This is saying S dot L is 0. In other words, if I measure the first register, then what should I get? If I measure the first register, I will get L such that S dot L is equal to 0. Here, L is picked uniformly from all such possible L's. Notice the amplitude for all L's which satisfy S dot L equal to 0 is equal in expression 1. Since the amplitude is equal, this shows the important fact that when I measure the first resistor, I will get an L such that S dot L is equal to 0, and each L is picked uniformly. Question is, how does it help? Clearly, L dot S equal to 0 gives us some information. It is some bit of information about S. Specifically, it gives me a linear equation. You might ask, linear equation over which field? This is F2 over F2. It is giving me a linear equation. S dot L is equal to 0. This would look like S1L1 plus S2L2 plus SKLK equal to 0, where this plus is addition mod 2. I'm talking about field F2. One linear equation can't help, but we know Gaussian elimination. So if we do it multiple times, repeat the algorithm multiple times, we will get S dot L1 equal to 0, S dot L2 equal to 0, and so on. S dot L G equal to 0. The claim is this can make us recover S. When can we recover S? Given a bunch of these equations, when can we recover S? So these are bunch of linear equations. If I have k minus 1 linearly independent equations, this will give me S. Great. So every time we did this step of making a equal superposition, querying, measuring the second register, then applying the Fourier transform. So every such iteration gives us an L such that S dot L1 equal to 0. And each L appears uniformly here. Now if we repeat it, we will get L1, L2, LG, and so on. To finish the algorithm, we need to show that if we do this algorithm, if we repeat this step, we will get k minus 1 linearly independent L's with high probability. Where, remember, our query complexity was log n. Each iteration takes one query. So we want G to be order of log n. Let me once write it again. What do we need to prove? I will call this the Simon's iteration, equal superposition, then querying the ith index, then measuring second register, all these steps. Remember, where did they go? Yeah, all these steps I will call one Simon register. This is the state which I get, which is also called coset state because of good reason. I will tell you next time why is it called coset state. But each time we repeat some iteration, we get coset states. But if we repeat it order of log n times with high probability, we get k minus 1 linearly independent L's. This is left to prove. This is a completely classical statement. This is done classically. Once we recover these L1, L2, LGs, then we don't have to worry about quantum computer. We just solve these linear equations. This is known as Gaussian elimination. We are going to do Gaussian elimination on a classical computer. Everything can be done classically. And the question is, do we get L1 to LG with high probability? And that we will see next time.